So in this video, we're going to solve the 2015 AMC 10A problem 19, and it's about triangle geometry. So it's a geometry problem. And as you can see, they didn't provide a diagram, but you guys should be able to draw diagrams according to the question. So the question says the isosceles right triangle ABC has right angle at C. So isosceles right triangle. Yeah, just drew the diagrams. You ready? Right angle at C, and area 12.5. Okay, and the rays trisecting ACB. So what it means by trisecting an angle means it divides the angle into three equal angles. So if you look at my angle bisector video, an angle bisector is a ray that divides an angle into two equal angles. Trisecting is dividing the angle into three equal angles. So it trisects ACB, these rays, and intersects AB at D and E. So we can just say this is D and this is E. What is the area of CDE? So, yeah, there are multiple ways to approach this problem, but in this video, I will show you a way to, a very creative way to approach this problem using really simple triangle geometry. So firstly, if we know that the rays trisect ACB, then these are 30 and 30. These are all 90 divided by 3, which is 30 degrees. So each of these angles are all 30 degrees. So I'll just label it for now. 30 degrees. Yeah. And then, so we'll just try to find all the information we can before we start. So firstly, this is an isosceles right triangle, and it has a right angle at C, and it has area 12.5. So we know that AC is equal to BC. So AC and C is a right angle. So AC times BC divided by 2 is equal to 12.5. So, but AC is equal to BC. So we can just let AC equal X. Just let AC equal X. Then BC is equal to X. So then X squared, okay, I'll just put this in a different color because, yeah, X squared divided by 2, so X times X divided by 2, AC times BC over 2. Actually, I'll just show my working out. So AC times BC divided by 2 is equal to 12.5. So, but AC times BC is equal to X times X, so X squared divided by 2 is equal to 12.5. So X squared, well, is equal to 25. Therefore, X is equal to 5. Pretty simple. So we found that X is equal to 5, so AC equals BC equals 5. So we can just say, we can erase this and just say that AC is equal to 5 and BC is equal to 5. Yeah. So, okay, we found some important lengths, but we have to find the area of CDE. That's the problem. And we can clearly see that since this is an isosceles right triangle, by symmetry, the area of ADC is equal to the area of BCE. So the area of ACD, the area of ACD is equal to the area of BCE. Yeah, I'm gonna say S, that triangle name, to indicate it's the area. And yeah, normally people use like square brackets and a capital A instead, but yeah, there are multiple ways to write it. So seeing this, we can see that basically if we just subtract, so the sum of the areas of ACD and BCE is just 2 times ACD. So the area of CDE is just the area of ABC, which is 12.5, minus 2 times the area of ADC. So all we have to find then is the area of ADC. So we're just going to change the problem to finding ACD for now, so that we can instantly find CDE after finding ADC. Yeah. So firstly, ABC is a 45, 45, 90 triangle because it's an isosceles right triangle. So this angle is 45. And what we're going to do is we're going to drop a perpendicular from D to AC. That was perfect. And yeah, perpendicular. And we're gonna call that F. So what can we observe here? So if we recap the special triangles, then if we have a 30, 60, 90 triangle, so 30, 60, 90 triangle, then the ratios of the sides are 1 to root 3 to 2. And then if we have a 45, 45, 90 triangle, then the ratios would be, not root 2, 1, 1, root 2. So these are the special triangles, the ratios. And these are called special triangles because the ratios are pretty straightforward. And as you can see here, so what we found is that after dropping a perpendicular from D to F, we formed a 45, 45, 90 triangle here and a 30, 60, 90 triangle here. Okay, I'll just mark it to make it clear. Yeah, so there's a 90 and a 30, so this is 60, and this is a 45 as well. So this is a 30, 60, 90 triangle and a 45, 45, 90 triangle. And this is neat because now we can just use these area lengths to easily find the lengths of some of these lengths easily. So firstly, we can find that AF, the ratio of AF to DF, since it's a 45, 45, 90 triangle, is 1 to 1, so they're equal. So if we say AF is X, then DF would be X as well. And then we know that CF would just be 5. It would just be AC minus AF, which is 5 minus X. So 5 minus X. And then one more thing we observe is by the ratio for the 30, 60, 90 triangle here, 5 minus X, the length opposite is 60. The ratio of the length opposite 60 to the length opposite 30 would be root 3 to 1. So 5 minus X to X is equal to root 3 to 1. So 5 minus X to X is equal to root 3 to 1. Oh, and then if we can see that this equation is going to give us the value of X. So 5 minus X is equal to root 3x by cross multiplying. And we get that, and then if we do this, so we get this. Okay. So X is equal to 5 over root 3 plus 1. And if we just rationalize it, I'll just skip some steps because most of you will know how to do this. It'll be 5 root 3 minus 5 over 2. Okay, it looks a bit messy. 2, yeah. So we found the value of X. And now, which is 5 root 3 minus 5 over 2. And we can use this value to easily find the area of ACD now. So the area of ACD would then be, let's see. So the area of ACD is equal to, it will be equal to base times height divided by 2. So AC times DF divided by 2. And AC is equal to 5. And I'll just put the half here. So 5 divided by 2 times DF is 5 root 3 minus 5 divided by 2. which is equal to, there's no space, which is equal to 25 root 3 minus 25 over 4. There we go. So we found the area of ACD. And now, as I said before, we can instantly find the area of CDE by minusing 2 times this area from the area of ABC, which is 12.5. And we're just going to write 12.5 as a fraction, so 25 over 2, because this is a fraction and we want to make calculations easier. So let's see, I'm going to use red. So area of, what is it, CDE is equal to area of ABC minus area of ACD. Oh no, 2 times the area of ACD. There's not much space, but I'll just try. Okay. So area of ABC, we'll just write it as 25 over 2 instead of 12.5 minus 2 times 25 root 3 minus 25. Oh, actually, I'll just simplify this straight away. So 2 times the area of ACD. So 2 times this would be this would be the same numerator divided by 2 instead. So and if we simplify it, we get 50 minus 25 root 3 divided by 2. Yeah, I don't need that tick. So we have found that the area of CDE is therefore 50 minus 25 root 3 over 2. And if we look at the answer choices, yeah, it's here. So the answer is D, 50 minus 25 root 3 over 2. And as you can see, there are some answer choices to take account for mistakes that you can potentially make in your arithmetic calculations. So yeah, that was a very nice geometry problem. So for those who are experienced with triangle geometry or trigonometry, maybe you would have used some sine or cosine formula for the area to find CDE like very easily, or maybe you didn't even drop this perpendicular. Maybe you just used some trigonometry formulas to straight away find certain lengths. But really, in this video, what I wanted to show is that is an interesting technique in triangle geometry. So basically, if you can find a 45 angle or 30 angle, then always try to draw your own lines, so that you can get some special triangles, and then the problem will get much easier. So yeah, so here we already knew we try to form these triangles by observing there's a 45 here and 30 here, and just drew this perpendicular. So this method is called using auxiliary lines, and it means like drawing your own lines to the diagram to reinterpret the diagram and make it a bit easier. And it's a really creative method to solve geometry problems, and that is what we use here as well. So yeah, hope you enjoyed this geometry video, and hope to see you in more of my videos.